Okay, so all right, so this is a sample that we just tested. You have all the geometrical properties and the value of the maximum force in order to calculate this fracture toughness. I'm going to give you a hint, okay? Just so you don't get the wrong value and you don't report the wrong value. The fracture toughness of rocks varies more or less from 0.05 to about, I would say, 1.5 or 2 MPa times square root of meter. This is a weird unit, but that's you should get the value in between these numbers, okay? And what I was telling you before is that now if we look at the surface of the fracture, you see it's not perfectly planar. So I'll pass this sample so you can take a closer look as we finish the lecture. You can take a picture too to include in your report. All right, so let me see where we continue. 79. So yes, you were raising your hand. Is there anyone? No.
This is due next week.
No, this is gonna be due. Let's do it. You have a homework to work on, okay? So let's do it after Thanksgiving. I'm going to add that date later on. So okay, we talked about this. We talked about that. Let's continue with another example. So now we know this theory about the Griffith theory. We can calculate, for example, what would be the expected width and expected stress intensity factor, let's say for a fracture which is 10 meters long. The minimum principal stress, in this case, which is going to be equal to S3, is going to be 20 MPa. And let's say that the fracturing fluid pressure is 20.5 MPa. And you are fracturing a rock which is relatively soft, just 1 gigapascal of Young modulus with a Poisson ratio of 0.25. I like that you tell me for a constant pressure in the fracture, I like that you tell me what is the width of the fracture in the middle of the fracture. I gave you the questions for that. And what is the stress intensity at the tip, of course, of that fracture. Okay? So if you didn't copy the equations, I'll put the equations in here, and I'll give you 5 minutes to solve this problem. This will give us an idea about what we should expect for the values of width and stress intensity.
Is PO just PF?
PO is the net pressure and it's a constant pressure. Yes?
When we're doing the pressure on the lab, what area should we use? Area of a semicircle?
What area?
We have the force, but we need to do net pressure, right?
You mean for the test that we just did?
Yes.
There is no area there. So the fracture toughness depends, is of course proportional to the maximum force. This is A.
Oh, that's just
Is the length of the notch. The length of the notch of the fracture and then you have R, which is the radius of the cylinder, and L, which is the thickness of the sample. So there is no area there. Anyone has a solution already? Remember that here you have to use the plane strain modulus, okay? It's not the same as the Young modulus. The Young modulus, if we come back to the beginning of the class, was you use it when there is no confinement from the side. This is not the case with hydraulic fractures. You have more rock around. So you need to use, in this case, the constraint modulus.
C is the same as XF, right?
Yes, but in this particular case, yes. It's a half length of the fracture. But XF is something a little bit more general. C is just for this ellipse, for the Griffith theory. Yes?
I got the width, maybe.
Okay, what did you get?
768.
7.7
.7.
meters?
Yeah.
That practically, I don't think that's correct. Anyone else got a different number? So we know this is going to be 4P0 C divided.
Is P0 20.5?
No, that's where the catch is. So for these equations, you need to use net pressure. In this case, the net pressure is going to be equal to 20.5 minus 20. That's what is really opening the fracture. 20 is just to get there, just to start opening the fracture. Those additional 0.5 are the ones that are opening the fracture. 15 what? So let me write this down. This is going to be 4 times 0.5 MPa times 10 meters divided here. This is 1 minus Poisson ratio squared. According to my calculations, this is 1.07 times 10 to the 9 pascals. Well, actually, no, this is going to, we can make it a little bit easier. I have megapascals over here, so this is going to be 1070 MPa, or which is the same as 1.07 gigapascals. All right. So what is that?
0.019
0.019.
meters.
I get 7. Are you sure?
0.019
Okay.
What I got.
Okay, let's say 1.9.
But I just used like 1070 instead of the exact.
Okay. All right. See, that's good enough. So, okay, how much is this? 0.019 meters. So that's about 2 centimeters, right? That's in the order of 1 inch. It's relatively very small. The width of a fracture is usually 100 or 1,000 times smaller than the length of the fracture. And this is the solution that you get here from this Griffith equation. All right, guys, we're a little bit over time, so calculate the Ki, and I'll give you the solution next time. But I have something very important to discuss with you, and this is